Today we're going to look at a multivariable version of Faa Di Bruno's formula. To begin, let's look at a relatively general example. Let f be a function that takes a real number as input and outputs a real number. And let g be a function that takes n real numbers, x1 through xn, as input and outputs a single real number, g of x1 through xn. Also, note that in this video, we're going to assume that we can exchange the order of differentiation when differentiating with respect to different variables. Let's differentiate the function composition with respect to x sub k1, x sub k2, and x sub k3, where k1 through k3 are taken from the integers 1 through n, and k1 through k3 are not necessarily distinct. What this represents is the general case of differentiating with respect to three variables, where we allow for repeat variables. After differentiating with respect to x sub k1, we get the following by the multivariable chain rule. After differentiating that result with respect to x sub k2, we get the following sum of two terms. After differentiating that result with respect to x sub k3, we get the following sum of 5 terms, where we have denoted g of x sub 1 through x sub n by the symbol g to save space on the screen. Interestingly, each of these terms corresponds uniquely to some partition of the set of integers 1 through n. Each term of a derivative corresponding to some partition of the integers 1 through n is represented by some configuration of dots in rectangular regions, where connected regions represent blocks of the partition and dots represent the numbers 1 through n that make up the set that we are partitioning. To take a little deeper look at the connection between set partitions and repeated differentiation, let's make a general observation about set partition. Notice that if we have a partition P of the set of integers 1 through n into some number b of blocks, then we can form a partition P prime of the set of integers 1 through n plus 1 by appending the integer n plus 1 to any one of the b blocks, or by placing it into its own block all by itself. Therefore, there are b plus 1 partitions P prime of the set of integers 1 through n plus 1 that can be formed from our partition P in this way. Also, if you're given a partition P prime of the set of integers 1 through n plus 1, removing the integer n plus 1 from whatever block it appears produces some partition P of the set of integers 1 through n. So every partition of 1 through n plus 1 can be generated in the way we just described from exactly one partition of 1 through n. Next, let's go back to the topic of differentiation. Notice that at the jth step of differentiation, each term is made up of a product of some number of terms, one of which is a composition of some derivative of f with g, and the others are derivatives of g. Let's assume that each of the terms at the jth step of differentiation corresponds to some partition of the integers 1 through j, and that each of the factors terms contain that are derivatives of g correspond to a block of the partition that term represents, with the order of the derivative of g being the number of elements in that block, and with the subscripts on k appearing in the dxk's, representing the integers between 1 and j that are contained in that block. Now, when we pick a factor to differentiate under the product rule, we're essentially appending the new element, which you can think of as the integer j plus 1, or the symbol dx sub k j plus 1, to the block that factor corresponds to, producing a partition of the set of integers 1 through j plus 1. Differentiating the remaining factor that makes up this term, which is some composition of some derivative of f with g, represents placing the new element into its own block by itself. These are the ways we just talked about for creating a partition of 1 through j plus 1, starting from a partition of 1 through j. When we do this over all the terms, we'll get a new set of terms that correspond to the set of partitions of the integers 1 through j plus 1. Each term will again represent a partition of the set of integers 1 through j plus 1. The factors that are derivatives of g represent a block of the partition, with the subscripts on the dx sub k's representing which integers fall into this block, and the order of the derivative representing the size of the blocks. Putting all these observations into a formula, we get the following, which is the multivariable Faa Di Bruno's formula. It says to sum over the set of partitions P of the set 1 through m, the product of f differentiated as many times as the size of the partition P, composed with our inner function g, and then multiplied by the product over the blocks B in the partition P, the derivative of g that corresponds to block B. The product operator that appears in the derivative is purely symbolic and has no mathematical meaning. It's just a shorthand for what elements of the set 1 through m are members of block B. Or in other words, it tells us what dx's appear in this derivative of g, and the superscript, which indicates the order of the derivative, is the number of elements in block B. This is all pretty abstract, so let's do an example. If f of x equals e to the 2x, and g of x1, x2 equals sine of x1 times x2, and h of x1, x2 is the composition of f with g, then let's find the derivative of h with respect to x1, x2, and then x2 again. Notice that in this case, m is 3. That's how many differentiations we're doing. And n is 2. That's how many variables we have. And our indexes k1, k2, and k3 are 1, 2, and 2 respectively. Let's begin by writing out the partitions of the set of 3 elements, along with the sizes of each partition. That is, the number of blocks in each partition. Note that the elements in each block of the partition correspond to subscripts on k, and the k's in turn identify which variable we're differentiating with respect to. For the first partition, this is the summand we are looking for. In order to simplify it, we need f prime of x so we can compose it with g of x, and we also need to find this g derivative. Since k1 is 1, and k2 and k3 are both 2, and since f prime of x is 2 times e to the 2x, this simplifies to the following. Next, we're looking for this summand. To simplify it, we need f double prime of x, and the product of g derivatives shown, which we can again simplify using the values of the subscripted k variables to get the following. Next, we're looking for this summand. We already have f double prime of x, and the product of g derivatives shown ends up being the same as before because of the specific values of the subscripted k variables. Next, we again already have f double prime of x, and while the product of the g derivatives seems different, they end up being the same again. Finally, to simplify this last summand, we need f triple prime of x, and the product of first order g derivatives shown, which simplifies to this. Summing all of these 5 terms, we get the desired derivative. Note that from each of the partitions, we constructed the corresponding term in our sum formula, and then we summed them to get the final result. To finish the video, let me give you an exercise. Convince yourself that, assuming we can exchange order of differentiation, the formula appearing in this video is equivalent to the single variable Faa Di Bruno's formula, which corresponds to the case that all derivatives are taken with respect to a single variable.